السلام عليكم.
وعليكم السلام.
عليكم السلام.
ايه الاخبار دكتور عمر؟
الحمد لله تمام. ايه اخباركم جميعا؟
الحمد لله بخير. كان ايه اخبار الكونفرنس الاسبوع اللي فات؟
كان انتنس قوي بصراحة، السيشن الايام كلها كانت يعني من 8 الصبح مثلا، البيسك كان ل 8 بالليل، وكان في سيشنز ل 10 بالليل. يعني it was very heavy، بس كان في good speakers. uh, David Baker actually gave a keynote presentation.
ايه ده الله.
David Baker اللي ما يعرفش he got the Nobel Prize for using AI in protein design the same year. اللي جيف هينتون برضو كان جيف هينتون أخذ النوبل برايز، كانت أظن physics، وديفيد بيكر got it in chemistry.
أعتقد كان السنة اللي فاتت تقريبا صح؟
Yeah, 2024.
مهم.
ده
مهم.
كان ذا بروتين سوسايتي، الكونفرنس بتاع بروتين سوسايتي.
ده كان one of the keystone conferences اسمه AI for molecular biology. ثواني I can share the link for the conference.
ده كان في سيليكون فالي ولا في حتة
كان
تانية؟
في لا كان في سانتا في، نيو مكسيكو. Um, where's the chat? Yeah, it was actually surprisingly heavy on the industry in terms of the attendance. There was a good mix of speakers from industry, like biotech startups, bigger companies. Um, One of the organizers is David Kelly, who was I mean, he had a good career in academia, but he's in industry now.
عقبالنا.
Mm. I have يعني اللي متابع اللي بيحصل في أمريكا دلوقتي، ترامب طلع executive
اتش 1
order
بي
ال H1B هتبقى
1000
آه،
دولار
ألف دولار.
100 ألف دولار، وفي كلام إن
15000
ال
دولار ديبوزيت على الفيزا.
السكيلد وركر فيزا برضه هتبقى تتحول
لا، هو في برضه كمان اللي أظن هتفرق بالنسبة لناس كتير، ال EB1 وال EB2
اه
visas. اللي عايز يبدلهم بال 1 مليون دولار فيزا والحاجات دي. يعني
دول
أنا
برضه للبندنج كيس ولا للحاجات الجديدة، بس يعني الناس اللي عندها applications مش.
I have no idea. I was supposedly going to apply sometime in the next few months، بس ما اعرفش الكلام ده غالبا مش هيحصل. ف
ممكن حضرتك
الله
ترجع
المستعان.
كندا بقى واجي اشتغل مع حضرتك، انا بعمل بي اتش دي هنا.
كندا فعلا فين؟
اه ويسترن يونيفرسيتي.
اه،
بس
ويسترن.
مم.
نايس. لندن اونتاريو، مش كده؟
اه بالظبط.
ماشي، بالتوفيق ان شاء الله. في ايه الفيلد بتاعك؟ هاجر صح؟ انا بس شايف
اه انا
الاسم ده
بفتح
هاجر. اه.
الكاميرا.
اه. ايه الفيلد
انا
بتاعك اهو؟
بايوكيمستري، يعني بحاول
امم
استخدم الديب ليرنينج دلوقتي في بروتين ديزاين.
انت في المكتبة، انا
اه
مم.
هي الساعة دلوقتي عندي زي لا حضرتك قبلي الساعة 12 ونص.
اه، نايس. طيب ربنا يقويك ان شاء الله.
شكرا.
دكتور معلش، هو حضرتك في كندا ولا حضرتك في أوروبا؟
انا في كاليفورنيا.
أوكي تمام. ربنا معاك.
امم انا الساعة عندي 9:30 الصبح دلوقتي. ف- طيب، النهاردة انا بعتذر، هنراب اب بدري شوية عشان عندي some family commitments الساعة 10:30، يعني هنخلص بس نص ساعة بدري. actually دي كانت البلان من الأول، إن السيشنز تبقى ساعة، بس somehow السيشنز بتexpand. طيب، حد عنده أسئلة الأول عن الحاجات يعني عدينا فيها الفترة اللي فاتت، ولا كله تمام؟ ده كله تمام، ولا ده الناس أصلا محدش بص في أي حاجة؟ طيب اوكي. um, let me share my screen طيب. اوكي. نظرا لانه we don't have that much time today, I thought maybe we just go straight to code, and then we have a nice topic and very important topic to cover. وفي نفس الوقت we will kind of jump between going over the basics of the topic plus implementing in code right away. Um, so last time we talked about the idea of cross-validation, and I think I spent some time at the beginning of the session trying to motivate the idea of why do we need to somehow control for the complexity of the model. And I gave an example of a super complex model that is overfitting to the data that breaks apart when we move to a different data set. And I give the opposite example of having an oversimplified model, which tries to, for example, fit a linear model to a non-linear problem. And then we proposed a solution. Yani we said it. How do we know if we're um, training an over complex model for a simpler problem or vice versa? Obviously, we can make some assumptions about the data that we're dealing with, but at the end of the day, it's very empirical how we optimize the architecture of the model given the data we have and the training objective that we have. And we introduced the idea of cross-validation as a nice framework to actually learn how well or bad the model is doing given the data itself. And the idea was we were splitting the data into test validation and train validation and test sets. And then we went through the examples of where is validation data being used along the process, where is test data being being used along the process. And we gave a nice example of how this is done in code. We ran through some examples using this through just Boolean masks and NumPy, like a very basic example or a very basic implementation of how to do this. And then we introduced the train test split from scikit-learn, which is the more popular framework. And then we talked about the PyTorch data loaders towards the end of it, and we rushed through it. So maybe we can revisit this today as we walk through code. So the entire premise of cross-validation is trying to solve the problem of overfitting of models. And that's only one of two ways in doing this. The other way, which we're going to discuss today, is called the regularization. And the concept of regularization, if let's zoom this in a little bit. Concept of regularization is actually pretty common in statistics as well, not just in deep learning and machine learning. And the idea is, I think, the closest to the idea of regularization, because the word, to me at least, is not very intuitive. The idea is we're adding some penalty term. So we would like, for example, the model to stay away from certain behaviors, if you will. And in order to force it to do this, we're penalizing these behaviors or these things that we would like the model to stay away from, so that you can imagine that. I think a good example would be like adding a magnet. So for example, we have talked multiple times about the idea of minimizing the loss, and we said a good analogy is thinking about walking downwards of a hill, for example, and the minimum that we would like to arrive towards is like the valley, so the bottom of the valley. And you can imagine that, and sorry, to keep the same analogy, we said the gradient descent algorithm is trying to guide us to what direction is going to take us to that bottom of the valley. But you can think of regularization as having a magnet, and whoever, like the hiker or whoever is walking downhill, is wearing like some shoes with metal, and that magnet is somehow pulling them, so that if they try to go in the wrong direction, then the force of that magnet is going to resist them from going in that direction. So kind of hand in hand with trying to look for the gradient and optimize for the direction where we're headed, we're kind of adding another layer of let's try and pull this person towards the bottom of the valley. So, some kind of just bullet points to work towards. So regularization, it penalizes the memorization of training examples, which I'm hoping is also um, something that you can intuitively think about. Um, Remember last time when we talked about the analogy of the when in the cross-validation cycle, the student who does like three levels of checking their learning. There's like the training part where they go and do their homework, and then there's like the assignments and then the final test. Um, and you can think of regularization down the same path or the same analogy as so that if your final exam or if your assignment is basically um, if you think about the student memorizing some questions from a question bank and then the assignment or the take-home test is going to be from these same questions, then the student is not really learning the subject properly. The student is merely memorizing some questions and their answers and applying them to the test. So just every time a new question comes from outside this question bank, if there's no good understanding of the concepts, then the student is just entitled to fail, basically. And this is a nice way to think about regularization that we're trying to penalize the model for memorizing the training examples too much. If I give the model a picture of a dog or a cat or a horse and expect the model to be trained to recognize a cat and a dog, we're expecting the model to learn features in a picture of a cat. So a cat has like a furry texture, has whiskers, has, not so long ears, for example. So if the model just memorizes the pictures of the cats that I'm providing in the training examples, and then anytime it sees a different cat, then it's not really a training to recognize a cat. It's just memorizing the pictures that were given during the training phase. Um, and then the other thing that we think about here is this is kind of a different way to think about the complexity, because the last time when I showed you the example in like the neural network, I was basically modifying the actual architecture of the network. So I showed you an example where like there's a super complex neural network with like 500 layers or something, 500 nodes. And it was overfitting to the training data very much. And then we showed like how if I change the data set to a different data set, how it performs poorly. So I was actually changing, like modifying the architecture of my network to get away from this complexity. But in regularization, you will see that we can not really mess with the architecture itself in terms of the number of layers and the number of nodes, but using the concept of regularization, we can try and penalize the complexity and force smoother solutions to the network. Obviously, this is the actual goal that we're trying to achieve. We're helping the model to generalize to the new data. And this is something we talked about. How would this affect the training accuracy? And I think, I hope everyone remembers, there is a general consensus that as you add more generalizability to your model, that you're actually harming your training accuracy, because in order for you to fit other data sets, you're kind of learning the underlying structure in the data, and thus your accuracy is going to move towards like you're going to move towards a lesser accuracy because you're not really trying to learn the noise in the data and rather the underlying structure. This is an important point that in regularization, we're changing the representation of the learning itself. We're changing the representation of the features that the model learn from the data. So a very straightforward example for me, at least, to think about is if we're, for example, trying to learn or trying to teach a model how to identify different cell types using its gene expression profiles, for example. Like we take data like RNA-seq data and try to teach the model, train the model to identify different cell types using the actual transcription values of certain genes. If you do an RNA-seq experiment or a single-cell RNA-seq experiment, you will find that you have something in the magnitude of thousands of features. So depending on, the depth of your sequencing, the experiment, your filtration criteria, whatever, you end up anywhere between 20 to 50,000 features per cell. And anyone could argue, I think, that not all these cells are important for the identity of the cell. So a T cell, for instance, would have a very strong reliance. Like when you identify its gene expression profile, you will see, for example, a lot of T cell receptor genes, a lot of T cell signaling features like CD3 components, for example. Whereas, a B cell would have more emphasis on the B cell receptor features or genes, right? So, in trying to learn the representation of a T cell versus a B cell, you don't equally treat every gene as important in identifying this cell. You would have to, or the model, not you, the model will have to change its representation, will have to change its way of giving importance to certain features, which we call the feature space, in order to identify different things. And this regularization, as we will see, is a very important or a very easy way to do this. It's a very important part of training because it's an easy way to do this. That's what I was trying to say. Okay, this is an important one because the examples I'm going to show you today are not going to be very convincing, and for exactly the reason that we're dealing and training really simple models. Like where the iris dataset, for example, that we've been working with is like 4 features. There's like 150 or 200 examples. I can't remember, but it's like this is really not the scale that you're meant to work with when you're training deep learning models. And I think we've talked about this many times that the actual strength in deep learning models come from the scale of the data that the model sees. The model needs really a lot of examples and a lot of training, a lot of examples and a lot of epochs until it learns the underlying patterns. And because we're dealing with very small models, because we'd like things to run faster and would like to just show like proof of concept. But the importance of things that we're going to describe today in the space of regularization are not going to be very evident from the examples that you're going to see. So I'm giving you this as a fair warning because then once we run the experiments and you see the results of how things look with and without regularization, it's not going to be very convincing. That's not because these concepts don't really work. It's because of the nature of the models and the data that we're just dealing with right now. But in real life, this is very, very different. Obviously, regularization works better with sufficient data. And again, this is the same idea like last time when we talked about the split of train and test and whatnot. You would still like the model if we're talking about penalizing certain things in the architecture or doing dropouts and stuff like we will just describe now. You still want to be you still want the model to have enough data even after you apply these regularization, because like we described last time, if your training data examples are all like 100 examples and you do an 80-20 split, for example, then you're throwing away very precious 20% of your data, and just keeping them as like a holdout data so the model never gets to train on them. The same idea if we're doing regularization and you're doing like a dropout with 50% or something, and you only have a very small training examples, then you're hiding too much of the training example away from the model, which is not too much to start with. Okay. Hopefully these are all clear concepts and hopefully tie nicely with everything that we've described previously. Um, there's three kinds of regularization. This is not very formal, if you will. Like, this is a nice classification that I've seen in one of the courses of deep learning, which kind of resonated nicely with me. So I thought maybe I present them here. because they kind of help you think about this in a very systematic way. That we could apply regularization basically at three different places when it comes to training the network. One is the node regularization, which you can think of this as a procedure that happens directly to the node itself. So, like, you think about your input nodes, your hidden layers and outputs. Um, the regularization in that space or in that category applies directly to the actual node itself, where the computation happens. The loss regularization is a regularization that happens during the computation of the loss function itself. So this has nothing to do with the data. This has nothing to do with the architecture or the nodes themselves. This only applies to the step where the loss calculation happens. And then the last part is the data regularization. And I think the name is self-explanatory. We're applying regularization to the data itself. And two examples here. We're not going to talk about data regularization today, but just to introduce the idea of what we could do to the data. One thing is very popular, for example, in the image space is called data augmentation. And the idea of data augmentation is you take one picture, for example, and you tweak it a little bit. So like you zoom into the picture, for example, or you flip the picture, or you change the colors in the picture. And the idea here is you're trying to tell the model, I don't want you to memorize this picture by itself, but if I show you three or four different versions of that picture, it's more likely that the model is going to start to pick up on the patterns, the underlying patterns in this picture outside of the, the noise, if you will, in the picture. And the other form of data regularization is called the mini batch regularization. We introduced the idea of training in many batches last time, but the idea here is you try to do a normalization within that mini batch, which is going to be different from one mini batch to the other. And because of this variation between mini batches, you're hoping that this is going to, again, confuse the model enough so that it doesn't memorize the data and rather learns the patterns within many batch. And once you generalize this to all the batches within the training process, then the model can more effectively pick up patterns rather than noise. Okay? Any questions so far? All right. I'm gonna keep going. So let's start with first the node regularization, which I think I mentioned this now many times already. The concept of dropouts. And the idea here is we are forcing the activation of certain nodes to be zero. So basically, you design your architecture. So you have, let's say in the iris example, we have four input nodes because the data has four features. And then you have however many layers as you would like as hidden layers and however many nodes per layer as you would like. The meaning or the essence of the dropout is that with every epoch of training, you give every node a probability to be set to zero. So when you set the activation of a node to zero, you're essentially forcing the node to act like it's not there. Because when the activation is zero, you're basically zeroing out the whole thing from the equation. So eventually we do a linear combination of all of these of all the nodes going into the layer afterwards. So if certain activations are zero, it's like these nodes never existed. And then when you go and do a back propagation, there's nothing to be learned out of these nodes. Does that make sense? This is very similar, if you will, to think about the dying ReLU problem that we described before, that because the ReLU is forcing things, the negative values to be zero, there's nothing to be learned at a node where it's consistently outputting a negative value because then the ReLU is going to change this to a zero and then the network doesn't really learn anything from this node. It has no contribution to the gradient. So, one thing to think about here, or one thing to uh, really internalize here, is that when we implement the dropouts, we give a probability, usually a fixed probability, to every node to be zero, and that's per node, not per layer. What does this mean? So, let's say I have a hidden layer of 10 nodes. When I say, for example, the probability of dropout is zero point 0.5, it doesn't mean that the probability of dropout across the 10 nodes is zero point 0.5, meaning that I more or less guaranteed to have 5 out of the 10 being switched on and the other 5 being switched off. The implementation here is that with every node, there is a probability of zero point 0.5 for that node to be on or off, which means that collectively, be okay. Another piece, the nodes don't know that other nodes exist. Like for example, in a hidden layer, the network doesn't have consciousness, so that the network doesn't know that there is 10 other, there is, if I'm a node in a hidden layer, there's 9 other nodes as well with me in that same layer. Every node is basically an independent entity, and it doesn't know that it's part of a network, and it doesn't know that there's other computation happening elsewhere. So every node then has a probability of being turned on or off by 50%. But because this is per node, you're somehow gonna end up with situations where sometimes the layer is gonna have only 30% overall activation or only 70% overall activation, or anywhere between basically 0 and 1. Because probability is per node, not per layer. Is this clear or am I confusing you? Clear. Okay. A very other important point is that dropouts don't happen during testing. So the idea of dropout is you are trying to, as the model is being trained, you are trying to, as the model is being trained, you are trying to, sorry, as the model is being trained, you drop out certain nodes because you would like the model to learn the features to learn the representation of the data, or to learn the structure in the data without relying too much on certain nodes. In other words, you're forcing the model to learn equally across the nodes, because in some epochs, some nodes are not going to be there, and the model still has to learn the underlying pattern in the data without relying on certain nodes, because at random with every epoch, some nodes are on and some nodes are off. It's like you're distributing the work of learning across all of these nodes. But when you come to testing the model, hopefully across all the batches, every node has gotten to learn, and every node now has a weight associated with it. And now, as you go and test the entire network, you would like everything to be on. So you would like all these nodes to be on. You don't turn nodes off when you're testing the performance of the model. Also, when you're using the model, so after you've done training and you have your model, now you would like to pass the data through the model and get your output, which is the prediction or the regression, or however, you would like to use the entire thing. But as you're learning, you're trying to force certain nodes to be on or off, because you would like to optimize during the training process, you would like to optimize how the model learns the representation of the data. Is this clear? This is very important, because then as we talk about another example, which is as we get to the L1 and L2 regularization, this is gonna be different. There's gonna be a very different implementation to how the network behaves in that regard. Um, yeah, so as I said, it makes the model, sorry, less reliant on individual nodes and forces a distributed representation across all the nodes. It prevents a single node from learning too much, obviously, because in one epoch, this node is on, and in the next epoch, it's off. So if there is one node that is learning a lot about the data and gets switched off, then the model performance is going to decay too much, and thus the model is going to correct itself over the following epochs. Obviously, similar to, like we said, that in general, the regularization overall works better with deeper networks and works better with more data and works better with more complex models. This still applies to the dropouts. Any questions to the general concepts of dropouts, or shall we just go directly to code, see how this is done?
Yeah, actually, I have a question.
Yeah.
So, if I understand correctly, so the point of the regularization is to also know the importance of each node. Is that correct? Or
No.
mm-hmm.
That well, um, to some extent, like the only thing that really can do this is the L1 regularization because it kind of forces the sparsity of the network, so it switches off some of the weights, but we haven't gotten there yet. But the idea of regularization is you're not really just learning the features, you're also trying to control for as I like for example in the dropouts we haven't really talked about the weights or the data at all. We're only talking about how much every node learns about the data. When it comes to L1 and L2, which is again a different form of regularization because it regularizes the loss directly, then it's a different story and they do different things to the weights as well.
Mm-hmm. Yeah, and the other question is like we are in the risk like to if we have like the distribution between 0 and 1 of
Mm-hmm.
switching off the nodes, we also like have the risk of the extremes of like not switching anything at 0 and also like switching everything at 1.
Yes.
So
So
mhm,
you decide what your dropout probability is. The default is 0.5% actually.
mhm,
But what I'm saying is, I think maybe I didn't say this very clearly. What I'm saying is when you say the probability of dropout is 0.5%, it doesn't guarantee that you have, if again, if you have 10 nodes within your hidden layer, it doesn't guarantee that you're gonna have exactly 5 nodes on and 5 nodes off, because the probability is calculated per node. So within every node, there is a 50% probability of being on or off. So eventually, when you do this 10 times, it could be that some 7 of them are gonna be on and 3 are gonna be off, or 7 are gonna be off and 3 are gonna be on. And you can test this by just, creating a simple network and setting the probability and every time seeing how many nodes are on and off. And you will find that the results vary a lot.
mhm.
But the thing is to realize is this happens independently within every epoch. So if you're training 1,000 epochs, for example, every epoch you initialize the nodes, there is a probability that every node is on or off. And once you average this across the entire training, then with some epochs, there's going to be a 30-70, other training are going to be 60-40, and you get the idea. There is some randomness about it that eventually, as it collectively trains the entire network, hopefully you regularize the whole thing. Again, it's very empirical in its nature. These are theoretical things that concepts that can guide us in how we're doing the training, but the actual, as you actually train the network, it's not going to be consistent between runs.
Okay, thank you.
All right. So, hopefully the code is now gonna be very familiar to you. I hope if you had tried to run some code and go through at least some of these notebooks. What I'm doing here is I am importing the libraries, I am loading the iris data set, and I am changing the labels from names to numbers so that we have the different readouts as 0, 1, and 2 rather than their names. And now I'm doing what we did last time of separating the data into train and test. And I'm doing this to the training data as well as the labels. We're doing this using the data loaders example. So I'm going to go over this because last time there was a few people that were confused. The idea here is PyTorch lets you build iterable classes called the data loaders. And these data loaders are basically, think of them as a special version of lists. So it's like an iterable is basically something that you can iterate through during the training so that you pull a single example or a few examples, a mini batch example, for example, and pass this through the model as it's training on them, basically. The iterables themselves, they don't directly, the iterables are not directly usable. So in order to, sorry, this is not the right way. The the iterables do not use the data frames or the NumPy arrays or whatever structure that you use to represent the data in Python. In order for data loaders to work with data, you first have to wrap the data into what is known as a dataset object. So there's two classes that you will find in PyTorch. One is the tensor dataset, and the other is directly the data loader. So you start by passing your data to this tensor dataset, which creates this dataset object in PyTorch. And this is the object that the data loader actually recognizes. So when you go and build your data loader, you don't really pass the NumPy array or the pandas data frame or whatever structure you have your data in. You first create this kind of wrapper structure around the data, which is called the tensor dataset. And then this tensor dataset can be passed into the data loader. Okay? So this is like a very streamlined, classic way of handling the data. You use the train test split from scikit-learn. You split your data into train and test. And the train test also lets you split the data into the actual data and the labels so that you have your X and Y. And then after doing this, you then wrap all the training data, which includes your training data and your training label, inside this dataset object, which again is just a container to represent the data. This is a structure that PyTorch would like the data to be in order to pass them into the data loader. And then the data loader is this structure, nice structure that now takes in, so now this training data, sorry, this train data here is the same object here that is basically the data set. And it also lets you conveniently set some parameters like the batch size, whether or not you would like to shuffle them. And you can check the documentation for all the other things that you can do with the data loader. It's basically a very, very flexible structure that lets you handle different kinds of data. Okay?
Does
Hopefully that makes
the
sense.
tensor data set looks like a dictionary?
I actually never checked. I don't know inside of it how they represent the data, but it's not a Python dictionary. If it's similar to how a dictionary behaves in terms of having a key and a value, that might be it. I never checked myself, to be honest. It never bothered me to check. I just know that this is a wrapper object that is needed by the data loader to load the data effectively. Good?
Yes, okay.
Okay, so this is also another way of building the model that I would like to introduce here because we've been using, like over the last few times, we've basically the couple of last times we showed how to build a model. We were using this sequential class model to build models. And as you get more complex with how you structure your models and you would like to predefine some attributes related to the model and whatnot, you start to use the concept of classes. If you're not familiar with this, basically Python is what we call an object-oriented programming language. The opposite of this is a functional programming language, which is more similar to R. But not to confuse people, R could also be object-oriented, and Python could also be used as a functional language. But that's not the focus of this, and that's beyond this class. What I'm trying to show you here is a different way of trying to build your model or create your model as a class. So instead of defining the model as an instance of this sequential class using this very simple format of just defining a linear layer and then adding like an activation function. And then in that case, we're adding a dropout to this layer and then adding another linear combination, which is here the hidden layer, which is here the hidden layer. And then we add a ReLU function, activation function to this hidden function, and then eventually just passing this to the output layer. This is how we initiated classes in the last couple of times. But now this is a different way of to actually design your classes. And this follows the principle of object-oriented programming. And the idea here is you start a class from this NN module. So you inherit all the properties of the neural network module, which is defined again in PyTorch. And this lets you do a few things. This is basically, I don't know how many of you here have used classes before, but this is how you define any class in Python. It doesn't have to be in the context of PyTorch or deep learning. Usually when you define a class, you have this init function, which basically defines a few things as you instantiate this class. And then you define some attributes and some methods associated with this class. A method is essentially a function that is just kind of tied to the class. So when you go and call them, you can just directly call the method on the class. So what we're doing here is we are, as we instantiate this class, again, it inherits from this module from PyTorch, which means that there's going to be some attributes that are by definition, we don't have to define them because they're inherited from this module. And you see that the definition of how we define our layers is slightly different. This is this is a definition of the definition of layers is basically something that you can control. So for example, I am calling here an input layer that is just a linear layer of 4 times 12. 4 again because we have 4 features, and 12 because I decided I would like to have 12 nodes. But you can do 64, 128, or however many you want. And I'm defining something called hidden layer. And here I'm defining hidden layer to be 12 by 12 because it has to be the input has to be the output of the input layer. And the output can be whatever I would like it to be. But let's say I would like to have a second hidden layer. Let's say one hidden layer has 64 nodes and another has 128. I can define a third layer here and I call it, I don't know, hidden 2 or something. And I can set it to whatever many dimensions as I would like it to be. I'm not going to do this here. And then I'm defining also an output layer. Again, the output layer has to have an input of 12 because this is the output of the hidden layer. And then we're basically having an output of 3 because we're classifying the iris dataset into one of 3 classes of planes. And then here is I am defining a dropout rate parameter. So every time I instantiate this class, I have identified or I have set it up so that it accepts a dropout rate. And dropout rate would basically be this probability that we talked about. So it's a probability for every node to be dropped out. This could be 0, which means no dropout happens whatsoever. This could be 0.5, which is the default. I am setting this to be an attribute or a property of this class that I can easily modify. And then I'm defining the forward pass as a method associated with the class. So every time I instantiate this class, it automatically instantiates with these parameters, being an input layer, a hidden layer, and output layer, and also a dropout rate, which I have to define. So I'm not giving this a default. So if I am to instantiate this with no numbers for the dropout rate, it's going to give me an error because it's expecting me to set this somewhere. So for instance, I could, if I do this, like if I do a dropout equals 0, then by default, this is going to be 0 unless I specify it to be a different number. Okay? All right. Hopefully this is old programming and not anything to do with deep learning. Now, the forward pass is exactly the forward pass as we described it before. The implementation is just slightly different here. So instead of using the ReLU method that is from the NN class, the NN module, we are using a different module here called the functional. So if you go up here, you will see that in the import, I am importing something called torch.nn.functional. And this is exactly what it says. These are functional implementations of some of the classes that are present in the NN module. This is kind of, think about it as like a slightly different API for the implementation of the same things, which lets you incorporate things like ReLU function and dropout function as standalone functions that you can put in your class as you please. Something to think about, so very similar to this, is, for example, the matplotlib library, which has 2 different APIs. There is the implicit and the explicit API. The explicit API was built to mimic the, what is it called? The MATLAB program, because people who moved to Python for plotting were used to MATLAB, and the kind of interface of the whole thing was supposed to mimic it. But because it's not very Python friendly, they came up with the different implicit API, where you have to predefine your figure and your axes, and then as you make changes to them, you're basically as if you're modifying the attributes of these figures and axes in order to change the plot. Whereas the plot class or the plot implementation is very explicit in that it just assumes whatever figure is open, it adds changes to that figure. So it's doing the same thing, but using a different API and different assumptions on your data. Okay. Um, so what we're doing here is we're defining what a forward pass does to the data. So whenever I call forward and I pass it an X, which is my input, it does these steps to me. It's like a function, but because it's attached to a class, it's called a method. What it does to the data is, again, it takes this input and it applies ReLU to it. So it applies ReLU to the self.input of X. So once X passes to so the self input, which is the input layer, you pass the X to the input layer, and then you pass this to the ReLU, which is exactly like these two lines here. And then we apply the dropout. So again, we call the dropout function from the functional module of Torch, and we pass it the dropout rate. So it takes this is P, stands for probability, of this attribute that we set up here. So this is self.dr dropout rate. And this could be whatever we define here, right? So this could be 0, 0 0.5, 0 0.1, 0 0.2, however you would like it. And then this is a very, very important piece to specify. And again, this has to do with the fact that we're inheriting the class from an end module. So basically what I'm trying to say here, or what I'm setting here, is a parameter called training. And this training is a parameter of the dropout function. And it tells basically the model whether or not we are in training mode, because the NN module by default from PyTorch comes with an attribute called self.training. And this self.training is basically a true or false parameter, which tells the model whether or not it's in training mode or evaluation mode. If you go back to the first time we talked about PyTorch, I told you that the network has some parameters in it where you could basically tell the model, tell the network whether we are in training mode or in evaluation mode. And we're going to see this in the training code coming up in a little bit. But this self.training parameter is basically a parameter that is found in the nn.module. And it's very important to set it here in dropout because, as we said, dropout only happens in training. So in order for the model to know whether or not it's going to do a dropout as it's doing a forward pass, because the forward pass also happens in testing, right? It checks whether the self.training is set to true or false. And if it's true, meaning the model is training, then it does the dropout. If self.training is false, then it doesn't do the dropout. Okay? Then we do exactly the same thing to the hidden layer, which is these two lines here. Yeah, and by the way, this is the equivalent of doing the dropout. So if you are using the sequential, after you define your linear layer, your input layer, you define your activation function, which is ReLU. Before passing the output to the hidden layer, you add in the nn.dropout with, again, the probability of exactly this dropout rate. The difference is because this is not class, this doesn't become an attribute of the class. It's just a standalone parameter that you set during the creation of this model. Okay, so hidden layer, the same thing here. So you, again, now for this hidden layer now here, so the input, the X that goes into the hidden layer, which is the output of self by default, is passed through the ReLU function, then subjected to the dropout function as well. Again, the same probability and the same idea of setting the train to self.train. And then eventually you pass your data through the self.output, which is this output layer here. And then you return X after having gone through the network. Okay, so this is basically a different way of setting up your class, your your network using the object-oriented programming and setting up your model as a class rather than as just an instance of this and on sequential. Any questions? Okay, hopefully that was clear. Okay, so after having defined our custom model class, sure you can come up with a better name. You now then define a network. So you instantiate an instance of that class using a certain dropout rate. And then you calculate the loss function, which in our case is still the cross entropy loss because this is a classification problem, the iris data set. And then we define the optimizer, which is the stochastic gradient descent with a certain learning rate. Hopefully this is old news now to you. And we pass the parameters from the network and the learning rate to it. And then we get, from this function, we get the actual network and then the loss function and the optimizer as like readouts. So yeah, in case you're not following, this is just a function to train the model. To create the model so that we can more easily pass this into the actual training loop. And this again is nothing new. We're defining a function to train the model, which basically just instantiates some empty vectors to keep track of the train and test accuracy. This is the bit that is very important. In the previous classes, we haven't really set any network to be either in train mode or in evaluation mode because we weren't really doing any dropouts. We weren't doing any regularization. So it didn't matter for us whether the whether the evaluation is on or off. Any model, when you instantiate it, is in train mode by default. You have to go and tell it specifically to turn on the evaluation mode if you would like something like the dropout to be disabled. So like in here, the self.training is kind of the model learns whether it's true or false because you set the training to be true. Sorry, you set the network mode to be in train or evaluation. So if I set this to .train, I'm putting my network in train mode, which would then cause the parameter self.train to be true. If I am putting my model into evaluate mode, then this is going to set self.training to be false and would thus disable the dropout, which is very important in our case because as we said, in order for us to evaluate the model, we're not really applying dropout. We only apply dropout when we're training the model. So these are the only two things that you will see different from the training code that we've run before. And we actually are setting train here, we're defining the mode of the model to be in train because at the end of the loop, we set it to evaluate. And in order for us, in order for the model to go back to train, we have to explicitly tell it to go back to train. So this will be exactly the same. Like if I don't really put it in train here and I just set it in train at the end of the loop, it doesn't really matter. By default, it starts in train, but once I switch it to evaluate, I have to physically switch it back to train. So one thing to do, not to get confused or forget, is to just switch it on at the beginning of the training loop or at the very end of the loop after you've done your testing. Either or, it's exactly the same effect. So otherwise, it's exactly the same as the training data, the training code that you've seen before. So you have your X and Y coming from the data loader that we defined. You pass it through the network, you calculate your loss, and then you do the back propagation. You set the gradients to 0, and then you do the backward, and then the step, you calculate the step, so you update your weights. And then these are just basically computing the accuracy of the training example so that you keep track of the accuracy. And then this is within every batch, and this is after the entire training is done. So like across all the mini batches. And then you move on to evaluation. So now we're switching off the dropouts and we're evaluating the entire network on the test data now. So this is that we're using this on the test data loader that we built. And now, again, we're just computing the accuracy of the train and test. Okay, so now this is just me setting out the dropout rate to be 0, so we're not really dropping out anything, and we're just training the model. As you can see, I ran this before. So as you can see, this is very similar to what we've seen before. It's a pretty simple model. It doesn't really need any dropout. There's no difference between train and test, meaning that we're not really overfitting the model. So actually, you don't really, if you look at this, you don't really need dropout, but we're going to do it for the sake of doing it. So what I'm doing here in this code is I'm going through, not going through, I'm setting a dropout rate list of basically from 0 to 1 all the way, and training a model with every one of those dropout rates. So if a dropout rate is 0, is 0.1, is 0.2, is 0.3, and so on. And with every dropout rate, I am creating a new model and I am training the model using the functions we just built. And then I'm looking at, instead of looking at the entire accuracy of the training, because this is a fairly simple network and it kind of converges well at the end, I'm just looking at the last 50 epochs to look at the accuracy across all these examples. We can do this across all of them, but it's going to be super noisy to look at. I'm just visualizing the last 50 epochs. And once you plot this, you get something like this. Basically, this is the dropout proportion. As we said, we have with every from 0 to 0.1 to 0.2 and so on until 1, we have 10 dropout examples. And this is the accuracy in the training data, which is in blue, the accuracy in the test data, which is in orange. The test is more is more accurate than the training data. Again, something you never see with real data sets, but because of the data we're dealing with here, this is just a very much an artifact of it. What you basically see here is as you increase, I mean, there's really no effect of dropout because the accuracy is already 100%. You can't really improve the 100%. But as you increase the dropout rate, more than 0.5 or so, you start to see that the accuracy is getting way less because essentially we're turning off way too many nodes in the network that the network actually doesn't have anything to learn from anymore. So the accuracy is getting really, really bad. So this is something to think about when you're using the dropouts, that with every data set and with every model that you're using, it's not going to be very straightforward for you to just say, oh, I'm just going to use a 0.5 dropout. This is the default because maybe in different cases it works okay, but it's not the optimal. The optimal is going to rely on your specific example, specific data, specific architecture, what you're trying to train the model to do. And this other plot here is basically a measure of the generalizability of the model, which is the difference between the train and test. So we kind of ran through this the last time when we were talking about the overfitting, that you can just check the difference between the test and the data to get a sense of how overfitting you are to the model. So I'm just plotting this for reference. Again, like I said in the beginning, these examples are probably not the best to showcase the effect of dropout because of the data and the architecture of the models that we're using. But nevertheless, you could do some playing around and trying to see the effect of these yourself, or maybe get some other data sets from Kaggle or something and play around with it. I'm pretty sure you can use the same code for them. You'll probably have to adjust the data loaders depending on your data set, but the same concept is going to apply. And then I'm also giving you kind of an assignment here to play around with. What happens if you increase the complexity of the model? So we set up our model with a hidden layer of 12 nodes or something. What if you push this to 64, 128, and then you start to do dropouts? My intuition, I haven't tried this myself, but my intuition is as you increase the complexity, you probably will go into the territory of overfitting. And then when you increase the dropout, then you can start to observe an improvement because on the test data set, because you will be dropping out some of these complexity in the model so that the model is going to generalize better. Again, with this data set, I haven't tested it myself, but it would be fun for you to try, I guess. Maybe it's also not going to help much because the data is very simple, but maybe it does. So something for you to play around with. Okay. I actually kind of have to go now, but I would like to very, very quickly introduce the regularization. Um, or shall we keep it to next time? We can keep it to next time because I really have to go. Sorry.
It's
Do you
okay.
guys have
Thank
any
you.
questions?
Thank you.
Is the code clear, or was it confusing now that we've switched to using classes rather than um, the sequential, the built-in sequential class?
It's clear. Yeah.
Any other questions? I yeah. يا جماعة الصمت ده. Okay. What I will do is I will upload the notebook to GitHub. And then you guys can take a look at the loss regularization. I actually only included L2 here. Maybe I will add the L1 as well. The L1 is a little tricky because it's not built into PyTorch. So we will have to manually do the math as we calculate the loss. And I was hoping to get through this today. And I was going to give you an assignment to implement something called ElasticNet regularization. But yeah, I'm not very fast in explaining, guys. I apologize. Okay. If no questions, which I haven't heard any, I will see you, inshallah, next time. Until then, please try to play around with the code. This is never going to make sense until you read the code and you try to do changes yourself and think about things and maybe bring in a data set that excites you. It could also be from a very different, like we're dealing with iris and stuff. You could have some sequencing data that you would like to build a classifier for cell types. I mentioned this example many times now. I'm hoping to, I don't know, excite maybe a few people to try doing this. If you have it in you, I'm pretty sure this is going to be a fun example. And if you run into problems, I can help you troubleshoot or debug. But it's up to you. You do you. All right. See you inshallah next time. Assalamu alaikum.
وعليكم السلام.